everyone and welcome to a new discussion which though we are going to continue discussion on this groundwater exploration, and this is part 8. In earlier discussions related with groundwater exploration, we have discussed certain geological conditions, and basically we are talking about subsurface geologic conditions. But to initially we have to also consider whatever the present on the surface of the earth or part where we are doing this kind of exploration, and try to understand maximum what we can extract from the surface information. And once the subsurface information or surface information is found insufficient, then we also go for subsurface investigations, which we will be discussing in later our discussions. So, first in simple dipping beds, now we can also discuss where the how the water is or groundwater is controlled by very well known geological structures, and one of them are the faults where there is a dislocation of beds. And as you can see on the right figure, if I take the bottom figure here, that what you see that this bed earlier used to be supposed to be here, now there is a shifting of this bed towards this, and likewise this bed has gone down. If it is an impervious bed or fine grained say clay kind of sediments, then we have to understand on a larger scale what would happen even in a local scale. So, what I am trying to say that if drilling is done on this side, then you will get, this is confining aquifer condition, then you would get water at this depth, but here if drilling is done, then water will not be available at this depth. In confined aquifer condition, it would be available here. So, a fault in between two bore wells can create a different depth for availability of water. So, faults and associate fractures. Fractures are or joints where dislocations are not there, displacement is not there. In very simple terms I am explaining, because those who do not have background of geology, then for them I do not want to bring too many details here. So, faults and associated fractures are important structural features that impart secondary permeability to the great depth to consolidated rocks, because these are zone of weaknesses starting from joints, fractures, faults. These are the zone of weaknesses, and zone of weaknesses means they will provide the secondary permeability. Secondary permeability in sense that the first permeability is within the rocks and secondary permeability becoming available because of these structures. These structures, faults and others are in because of some tectonic activities or maybe some erosional or weathering activities, but most of the time these are related with tectonic activities which generates faults, but some fold and other things are also very slow activities which can also create faults and other geological features. So, the presence of fault is commonly indicated by a line of springs. So, on surface or sometimes in a section, you can see that on surface the water might be oozing out, seepage might be there, or even a spring might be there, or a artesian condition might be there. And also in the section you may find a spring, water is coming out of surface, and displacement of beds, as I have earlier mentioned here, that displacement of bed is there, and maybe some other formations like breccia and other things which are coarse grained sediments, and which can give a better conditions for groundwater point of view, and may provide the better permeability for the flow of the water in underground conditions. Further, in the faults also bring when they are into juxtaposition of permeable zones against the impermeable zones, that may act as hydrologic boundaries of aquifers. As we are seeing that if suppose this fault zone which is there, which is having a secondary mineral, if it does not allow water to flow from one horizon to another across it, then this can become a hydrologic boundary for us. So, a permeable zone of different stratigraphic positions against each other that establish the continuity. So, faults are, as we have seen, that when faults provide the permeable and relatively impermeable formations are juxtaposed, positive and negative sides are formed related to each other because of shifting of different beds or formations, and this may bring about abrupt change in the production or salinity. See, productivity, which is related with the quantity of water, salinity is related with the quality of water. So, because of the faulting, suddenly one may get even a saline water also, depending on how the water is stored in subsurface conditions or how aquifers are formed at a particular location. Now, there are two sides generally in a, if we see this one, that this is a down throw side and this is relative to this is up throw side. So, in down throw sides the scenario is going to be different than compared to up throw. So, down throw sides of fault may receive coarse grained debris derived from erosion of uplifted rocks. So, from other side also the material can come, and there are some certain areas which we can think in that direction, like this is the geological map, of course, this is surface map, not the section. Geological map of Narmada river valley, where you can see that a lot of quaternary sediments, means younger sediments have deposited, and of course, there are some active faults are there and so on. So, these are the quaternary sediments, they and these are the fill, or we say alluvial fill, and they are very good from groundwater point of view, because so sediments of hundreds of meters may accumulate in down faulted basin, because when there is a faulting, then one down throw side will go down, it may become a basin, and which we are calling here is a down faulted basin, and then there might be filling of sediments which even come from the up throw side, and that will be deposited, and similar kind of sediments which has been deposited in Narmada river valley are shown here in dark grey color. So, in a many faulted regime or many faulted areas where such situations is there, you may find on one side of the fault you are having quaternary or younger sediments or alluvial fills, and from groundwater point of view this is very good. Just recall what we get in Indo-Gangetic plain also, the alluvial, and these alluvials are very good even if you are having unconfined aquifer conditions, does not matter. So, the lot of water availability is there, and these areas are very fertile land also, because the water is available, soil has developed, and so therefore, these areas have become very fertile also. But if in case of when we are dealing these faults or uplift block of a fault in a coastal area, then these arrangements of pervious or impervious rocks may prevent seawater intrusion into freshwater aquifers. But a reverse scenario can also happen, that a seawater can, because of this faulting, seawater can get intruded into groundwater. So, therefore, study of such structures, geological structures are very important to know that which is down throw side, which is up throw side, whether in coastal areas the water will enter or seawater will enter in the groundwater or it will intrude in the groundwater, if a reverse scenario. If it is a reverse scenario, then it is much safer. But if it is seawater is entering in groundwater regime, then there is going to be a big problem. Now, there are another very important geological structures which exist in various places, and which are mainly in the sedimentary rock regimes or in metamorphic areas. So, these folds are also play very important role from the groundwater exploration point of view. So, we know that if a series of strata everywhere has homoclinal attitude, that means that if strata are completely horizontal or dipping only on one side very in the same manner, then the distribution aquifer can be predicted by simple measurements of attitude of surface on the basis of information as shown here in this 3D diagram, that we can very easily assess using a very simple technique which is called 3-point techniques, or with 3 wells data we can know that what is the how the beds are dipping. But if it is not homoclinal, that means everything is not inclining in the same direction in the same way, then challenges becomes. This is the example in earlier discussions also. We have taken this example. These are the examples of homoclinal dipping beds, where you are seeing that pervious or impervious layers or fine grained or coarse grained layers are dipping in the same manner. There is no changes in these. So, these are, in that way the prediction becomes much easier. If we are having a information of well at this direction and also the dip direction, dip amount, then we can predict that what would happen at this location, because they are all dipping in the same way. But if it is not the scenario, then we may find a lot of difficulty. This is another example of homoclinal sequence, but this section is completely different. That was a that was a section in the, or we say dip section. Here you are seeing a strike section here. So, this is again the fresh exposures of Shivalik rocks along Chandigarh Saharanpur road section. You can see very easily that in this section you are having fine grained rocks, and on top and bottom you are having coarse grained rocks. So, this kind of area, and it seems that these beds are dipping towards the screen, or what you are seeing here, or away from the road, which road is one part of the road is also seen here. So, faults plays very important role, and while doing this kind of investigation from groundwater exploration point of view, this knowledge is very important about that particular location. If somebody is working in a granitic terrain, then you may not encounter such kind of structures. But if somebody is working in sedimentary or metamorphic terrain, then one should be completely aware and should have all knowledge. And this knowledge can be collected through the measurements of these basic data, that is the attitude of bed, that is dip, strike and plunge and other things related with bore holding, and a lot of prediction based on this superficial data about subsurface geologic condition can be made. So, this dip of strata, greater depth may be different from that one exposed, hence the surface observation may not be useful prediction without additional subsurface information. So, sometimes you may encounter this kind of situation where you are based on the superficial information you are predicting something, but it is not fitting in subsurface condition. So, one thing which we have also discussed in earlier discussion, that another solution is to create as geological cross sections. One of the examples here through these 3D diagrams, or 3D diagrams are shown here, that this part is representing a geological cross section. So, on surface you are getting some limited information, but based on the attitude of beds and other data, when you plot them and you get a geological cross section, then you can understand things very easily. Like here it is understood that there is a normal fault and piezometric surface, different rocks are there, or how they are getting connected with each other, that or change in phases can also be seen. Similarly, here you are having folded sequence, and so in the section you are seeing folded sequence, but on surface you do not have much information except the attitude of beds. So, based on that information one can get. However, as mentioned earlier, that sometimes whatever you are seeing on surface, that is the attitude of bed, may change at greater depth, and sometimes when your geological cross section, your surface information all are giving or failing, then the final resort is of course additional subsurface information, and for which next step would be geophysical exploration. And even that is not giving good understanding about subsurface conditions, then finally we go for a expensive solution, which is test drilling, which we will be discussing also later. So, now further we continue with the fold, and what you are seeing on the figure is again a section, and here you see that if I see the water table is here shown here, and if I go and see at different depths I am encountering, like here A and B, I am encountering the same bed, but it is folded here, it is folded here, and as it is shown here. So, sometimes we get sort of confused at the top part we are getting the same formation, another again we are getting again. So, generally it may be due to folding, and that this is what the caption mentions, the control of folds on groundwater occurrence. Borehole showing, this borehole showing repetition of aquifer A or that bed lower down at B due to the overturned fold. So, a different kind of fold, which is again it is repeating the same aquifer or same bed. So, sometimes we get these kind of situation, but this is in case of a well. We have been so far discussing about surfacial information, but anyway, if such sections can be prepared before any drilling, then that is more cost effective. So, if the strata are folded, as in this case, either into syncline or anticline, like here it is a synclinal situation and here it is anticlinal. Generally these are in repetition mode, that first is syncline, then anticline, syncline, anticline, like this. So, syncline and anticline, the aquifer distribution becomes more uneven and complex, and more detailed subsurface information is required in order to understand the entire distribution of aquifer in subsurface condition. That is, so in a folded regime, in a folded geological setup in any area, such kind of care is very much required. One is expecting water, groundwater at certain level, but you are not getting, or at one is expecting groundwater at maybe very high depth, but you are getting at a shallow depth. So, these may be because of folded regime. Like here, if a borehole is done here, then I will get I will encounter aquifer at a very great depth, but if it is a antiform or anticlinal, then I will get water here, and even I may have a situation artesian if the piezometric surface is going like this. So, depending on this geology, and of course, that here the topography is also playing important role, and then I may get different situations. Geological settings yielding artesian conditions, folded and fractured sedimentary rocks. So, sometimes these folds can give you artesian conditions, sometimes these folds can give you much more water at much more depth. So, prior information, prior understanding about this kind of regime, folding regime, if that is available, then our understanding of that area, our prediction about the availability of water becomes much easier. So, in region of water folding, the water table may cut across a series of folded beds, as you are seeing on the right side, and in this way the permeable bed may in some places be in the zone of saturation, and in other places may be zone of aeration. So, here this is the permeable bed is being in the near the zone of aeration here, and therefore, you are having a artesian condition. So, aquifers of the same stratigraphic horizon may be repeated due to overthrust of folds or overturned fold. So, in earlier examples I have seen, or artesian conditions, flowing wells are also likely to be obtained in synclinal structures and then in anticlinal structures, depending on what kind of topography top of which it is there. So, another type of geological feature or structure, I would say, is important from groundwater prospecting point of view, groundwater exploration point of view, and that is the unconformity. Unconformity basically represents the break between different horizons or maybe two horizons, which are top of each other or side by side. So, this is another structural feature that has an important effect on groundwater occurrence and distribution of aquifers in unconformities. Now, this an unconformity basically may represent the lack or deficit between the formation between different periods. So, there may be a time gap in the formation of rocks or maybe because of other reasons, and a completely different setup one may encounter. So, and mark the erosional topography of the older rock surface on which the younger formations were deposited. So, you are having very old rocks like very old rocks like Archean rocks or that kind of rocks, and Precambrian rocks, and suddenly you get very young rocks of Eocene and other time. So, that means there is unconformity in between, only erosion has happened, no deposition has taken place. So, example is shown here, erosional surface is there, then deposition has taken place. So, such kind of unconformities are there, and from groundwater point of view it is very important, because here you will not get much water, but here suddenly in this part you get lot of water. So, there are different type of unconformities people have identified. One is called disconformity, another one is called angular unconformity, and non-conformity. So, here what you can see in disconformity, that there are completely different types of rocks, and this is going like this. So, this is called the unconformity or unconformity surface. Here angular unconformity, the top layers are horizontal, you are assessing based on whatever information available on surface, but in subsurface the rocks are completely dipping in a or homoclinal beds are there. So, therefore, if I go for prediction based on surface, then I will be encountering some other rocks, but here situation is different because of unconformity. Similarly, here in unconformity. So, an unconformity I have earlier mentioned is a break in time, a time gap in the formation of different rocks, otherwise continuous rock record. An unconformity are a type of geologic contact, as you are seeing here also, and a boundary between rocks caused by a period of erosion, like here that there were a gap, no formations were there, erosional activities or weathering erosional activities were happening, and then because of some changes in the basin, the sedimentary accumulation starts and that deposited, and that creates a new surface, new sediments, and that becomes unconformity. So, unconformities may mark changes in lithology and continuity of aquifers also, and that creates a unpredictability or unreliable information if collected from the surface information. So, of the several unconformities, several types of unconformities, the stratigraphic column, that means from if we go from bottom to top, the most significant is one with the crystalline basement, as you can see here also, and rocks that younger ones, which is usually the lower limit of the productivity. So, here if a well is dig, then this is the lower limit of availability of water. Then you are having basement rocks might be a granitic body, no weathering, no erosion, nothing. So, no possibility of getting water in that depth. So, if it is drilling is done, test drilling is done, then after a series of younger beds from the top which will one encounter, and when it reaches the base level or basement complex is reached, the prospects of finding water at greater depth are very poor. So, myth exists that in the normal or common people, that if you do more drilling you may get water at greater depth. It is not true. It all depends on geologic conditions. So, depth is not that important as understanding of the geologic conditions of that local area. Even if it is rightly sited, a well is rightly sited, if that choice is there, then water for all the time may be available even at a shallow depth rather than going for deep wells. So, these unconformity are also caused, as mentioned, that erosional surface is commonly covered by coarse deposition of younger series, which are generally productive, as here also you can see that there are certain younger sediments are there, older sediments, and some sequences are there. So, see here, here the water table is shown here this with this line as you can see here, and there are different belts which are shown. Now, here you are seeing the depositions which are younger, or then of course, the youngest one you are having quaternary, Oligocene, Miocene is there, and where you are having well, that matters. Where you are having well, accordingly you get the water or availability of water. So, water level in different, these are shown, the water table is also shown here. So, this is because of unconformity. So, unconformity may mark the presence of fossil soils and productive layers between basal flows. So, there are different types of unconformity, 3 types I have already discussed. So, depending on what kind of arrangement of different rocks are there and what is the age difference and breaks because of some other things, different kind of water level at different depth may be found. So, younger beds above an unconformity may either recharge the lower beds of insulated them depending on their permeability. So, here what you are seeing that water is available at a shallower depth and need not to go at deep. Here we are going at a deeper layer because these are very younger rocks may have higher permeability than the lower one. So, with this we end this part of our discussion on geological exploration part 8, and in next we will be discussing furthermore about the exploration in part 9. So, with this I thank you all.